Hello, Chan. Can I start now? Okay. Good afternoon, everyone connected here. It's my time that we start our today keynote section. I take this opportunity and it's my pleasure to introduce Professor Dr. Volker Ezell, University of Adelaide, Australia. Professor Dr. Volker Ezell studied chemistry at Mainz University in the year of 1993. Our today keynote section. I take this opportunity and it's my pleasure to introduce Professor Dr. Volker Ezell, University of Adelaide, Australia. Professor Dr. Volker Ezell studied chemistry at Mainz University in the year of 1993. In 1994, he entered the Institute for Microtechnique Mainz. In 2002, Professor Ezell was appointed. And it's my pleasure to introduce Professor Dr. Volker Ezell, University of Adelaide, Australia. Professor Dr. Volker. Can I start now? So, good afternoon, everyone connected here. I take this opportunity and it's my pleasure to introduce Professor Dr. Volker Ezell, University of Adelaide, Australia. Professor Dr. Volker Ezell studied chemistry at Mainz University in organic chemistry in the year of 1993. In 1994, he entered the Institute for Microtechnique Mainz. In 2002, Prof. Ezell was appointed Vice Director R&D and IAM, and in 2007 as a Director R&D. In 2005 and 2011, Prof. Ezell was appointed as a part-time and full professor at Eindhoven University of Technology, Netherlands. In 2018, he was appointed at University of Adelaide, Australia, as a Deputy Dean at ECMS Faculty and Pharmaceutical Engineering. He was an honorary professor at TU Darmstadt, Germany, 2009 to 2018, and is a guest professor at Kunming University of Science and Technology, China. Professor Ezell is published more than 460 peer-reviewed articles, and his H-index is 57. He received his ASCH Award, Excellence in Process of Development Research, in 2007, and was Grant Novel Process Windows in 2010, the ERC Proof of Concept Grant in 2017. So with the long list of his achievement and glory, I would like to invite Professor Dr. Volker Ezell, please put a light on the topic, economic and environmental assessment of small-scale plasma-assisted ammonia production pathways.
Yeah, dear chairperson, dear Suresh, thank you so much for the introduction and thanks for the organizers to allow me to speak. Greetings, good afternoon from Australia, and I share my screen. And while I'm doing this, I can say that I know Malaysia and Langkawi Island very well. I was there with 28 students for 2 weeks and visited quite some universities in Malaysia and also some companies. But now my screen should be visible, and if not, let me know loudly, and I put it on screen. So let me go back. I like to talk about a new business model enabled by plasma catalysis and enabled by nanotechnology. That is the connection to the conference. We make ammonia on a local scale. You know, now it's made in world scale plants, and we make it next to the pharma by new technologies. So that is a disruptive model. I'm at the School of Chemical Engineering, and later you will see why I mentioned my function as research director of the Anti-Autonomous Center for Space Resources. Now, our idea sounds game-changing, but also a typical idea which scientists do, but I oppose to that. I like to give credits first of all, to the scope project, which was mentioned, which is ERC Synergy. That's the highest excellence which you can get in Europe. But then, most importantly, we are well advised by industrial leaders. First of all, Jürgen Lang, Evonik, that's a major specialty chemical company on the non-thermal plasma, and I will come to that. Chris Mesropian from Monolith companies, they revolutionized hydrogen making with thermal plasma at this point of time on an industrial level. Greg Butler, in simple words, the chief of the farmers here in South Australia, so the head of the South Australian Farmers Organization, and the company founder, Clean Carbon. And Lawrence Curtin, who is from the energy field, because obviously you can use ammonia for fertilizers and for energy. And Peter Wadowitz from Peat Soil, that is a local agricultural company here, and he received recently a high Australian award on the Queen's birthday list. So these are quite well decorated people with whom we work together, and some more people. I'm also part-time professor at the University of Warwick, so you see the affiliation. So we work based on, I have to go back, jumps a bit, based on industrial advice. And you see we started with Evonik to develop the business case, fertilizing with wind. So we use wind as an energy, renewable, and we make the fertilizer, in this case, nitric acid out of wind, because in air you have everything to make nitric acid. You have oxygen and you have nitrogen. You can find this on YouTube video in internet if you want to see that. And you see in 4 years, this has become very sincere. In 2021, so now we have a project of the South Australian Grain Farmers Association, and we work together. If you see our partner there, Nicholas Mumford, he's a change manager in big petrochemical companies, so he knows how to change the direction of big petrochemical companies. And above is Greg Butler, the local chief here of the farmers in South Australia. Now, on top of changing from a central to a local production, that's only what I talk about, I like to mention that we also work on a circular model of this kind of new production model that is given here. And I don't go into details. We published that recently, as you can see here. The main idea is that fertilizers make food. That is, you can see on the right side, and on the left side, you see animals eat the food, and the animals make manure. And then by the steps which are of relevance here, biogasification, biomass gasification, hydrogen making, in this case by thermal plasma, and then ammonia making by low thermal plasma, you come to a circular process. So this is a big picture, but this presentation focuses on the steps which are marked red here, the plasma steps as evident. And the basic model is shown right. So we go from the fossil energy to renewable energy, make hydrogen, because you cannot make green ammonia if you don't have green hydrogen. Hydrogen has such massive impact. So we have to consider both processes. Now, Australia is large. To give you a little bit idea, if you have not seen Australia, it's roughly 4,000 kilometers in all dimensions, yeah, from south to north and from west to east. And 50% is farmland in South Australia. So it's one of the major market fields for Australia. And just to give you an idea, Europe without Russia is smaller and has a smaller share of farmland. Now, what do we mean with local and at farm? And again, I like to show you a map. Now, every fertilizer, or almost every in Australia, is made by Yara. The company who does it here is called Incitec, and they sit in Pilbara, that is Western Australia. And they distribute it all over Australia, and a little bit is imported still. What we consider is a regional plant, and that is what I talk mainly about today, because that is the next step, and that's already quite revolutionary. So we go by a factor of 10 down in productivity and might have 10 regional plants, to give you an idea. And that is here the state of South Australia. Then we can go to a local plant, that is the larger Adelaide area, the metropolitan area and surroundings. And finally, we can go to one of the famous wine regions here, and I come back at the end to this. Now we make a holistic view, a supply chain. What I show here is basically textbook knowledge if you're familiar, but for those who are not familiar, you have a supplier. So that is a supplier of methane, then you make hydrogen and you make ammonia, so in 2 factories. They can be both distributed or just one of them. Then you have warehouses, you have transport in between, which is not shown, and you have the market, that is a farmer. So that is our way of thinking. How can we change that? Now, the main thing which I present here, also we think much wider, is to go from the Pilbara plant. You see S and P in Western Australia, so on the left side, that is the situation now. And we have 5 major farm regions, and they are supplied by them. And we think now about the local model where we have at this 5 or 6 regions, or only some of them, that is what we have to determine, local plants. We go even further in the thinking, and I will show this, but all the modeling shown later is focused on that. And just to give you an idea, Australia roughly needs 1.6 million tons fertilizer per year. That's quite something. And you see the regions naturally differ in their demand, but there is a demand of 300,000 tons per year in several of the regions. Now, which scenarios do we consider? I think you're all familiar with the Haber-Bosch process, and steam that hydrogen is made by steam reforming. That is the base case. And then we have the modern scenarios. My colleague and research partner, Professor Gente, spoke yesterday about that. The renewable energies, which then goes to electrolysis or the high temperature plasma. This is this TPMP, what is denoted here, means high temperature plasma. And then we need a mini Haber-Bosch plant, or very optimistically, our low temperature plasma reactor. So we looked at those combinations on a regional, local, and on a farm mobile scale. And what we considered is given here. And finally, we have, that is a vision of Evonik, they call it chemistry on wheels. It's a chemical factory on a truck delivering the farms. That is the most revolutionary approach. And finally, now electrolysis works well. It's available on a pilot scale, but in Queensland here, so in East Australia, they built a 3 gigawatt plant, which probably is one of the largest of its kind, with thousands of solar panels and electrolyzers there. So that is not a world-scale ammonia plant finally, but it's not so far from it, which is done in Queensland. What you see here is in USA, in Nebraska, that is the farmer state in US, Monolith company, I mentioned them, they make thermal plasma. I cannot go into details of the plasma technologies because I want to focus on the supply chain. Basically, you make methane, you have methane, and you make an activated carbon out of it, which is a very valuable material. And in a way, hydrogen is only the side product, cost-wise, but naturally a very valuable side product. And that works 100%. And here's a way of Monolith. You see, they're very ambitious, and they go the Olive Creek 2 plant. That is equivalent to 250,000 tons urea if you go from ammonia to urea. So you see that is a plant not so far from world scale. The thermal plasma is competitive. It's turquoise hydrogen. It's not as good so far as the electrolysis, which is the green hydrogen. So it has still a bit carbon emission, as you see here, but the hope is that gets negative in future. But even more important, it is 6 times better in terms of hydrogen production per kilowatt unit, or if you, as it's given here, 6 times more energy efficient per kilogram hydrogen. And then we have the container vision of Evonik, and that is not just vision. Evonik built such containers shown here on a truck. That is a final vision, but naturally a very costly vision at that point of time. Now, what do we do in terms of technology when we don't consider business models? We do also technology. We do the non-thermal plasma for ammonia, and also for nitric acid, that are the main fertilizer. That was started in the EU project MAPS in 6-7 years ago. Then I start with plasma. You see a gliding arc plasma, and the little wire in between, that is the plasma arc. Now, in the SCOPE project, we miniaturize that. We will have nano catalyst coatings. The dimensions which you see here, that is just 1 millimeter, and the pyramids are just 1 millimeter high. and we will investigate there a massive energy intensification. We hope that leads us to a more energy efficient microplasma, as we call it. Now, when you want to be successful with the farmers, you have to speak their language. You have first of all to know about soils, and that is a picture from Craig Butler, who is the head of the farmers. And so this combination makes you successful, the combination of technology, of business models, and knowing what are the consequences of different kind of distributions of fertilizers, and that we have in a team. Now, we don't make desktop studies. We go to the farmers, we go to the farm fields. This is Peter Wadowitz, the decorated entrepreneur. Here you see Craig Butler, and that is a real Australian farm. The farmer is the one in the orange suit over there. And Lawrence Fulcheri from France stands right, and he made the contact to Monolith. So this is a global interaction, and here we look a bit on the roots, how they develop in the very dry Australian summers. Now, coming back to some results. This is a life cycle plot, and I know that this is an overkill if you're not used to analyze that. What you see left are about 20 life cycle impact categories, and above we all know global warming. And then we have the color coding, and that shows out what is responsible. So we see the absolute value, and we see what is responsible for it. And two things to learn here is the SMR process, or the steam reforming process. Green has a massive impact, the hydrogen making, and the second thing which has a massive impact is road transport, over 4,000 kilometers. Transport makes 12% of all world energy. That is massive, and it shares, here we give 25%, but actually 30% of all the energy of the fertilizers go in transport. So question is, can you do that better? Now here we see again the same scenario with different plants, regional scale, farm scale, and we see it with classical energy. The answer here is clearly no, that does not work. Impact is too much. Now, if we take a renewable energy, you see you save up to 90% of the impact categories. So we all know that, but that is a proof that renewable energy can massively change those technologies. Now, just to show, I will show you transportation and modeling, that we don't use just lump sum values as given in the life cycle modeling softwares like EcoEvent. We consider real Australian trucks. Yeah, EcoEvent considered what is given on the left side, but we consider load factors and all kinds. The truck has to go back and it's empty then. And we have here the Euro classes, and there are Australian classes. And that makes quite a difference. That makes our simulations better, more realistic than the databases, which are sometimes 5 years old and costs have changed, for example. Now, this is the elevation profile from west to east in Australia, and we consider that. That is in our calculation. It's a difference if you climb over the Himalaya or if you're in a very flat country, what is the tons. Long story short end, you could save 800,000 tons of CO2 with our technology if that would be consequently taken. And we see it's 30%. I already mentioned that, and you see how much CO2 per ton ammonia. We also have other good effects on marine eutrophication and all the life cycle categories, as you see, so we can massively change it. So local transport is better and brings environmental benefits. That's the conclusion. Let me give a last plot on renewable electricity shown here. Now we compare all the technologies. Here left, the classical Haber-Bosch technologies, and the thermal plasma with mini Haber-Bosch, electrolysis with mini Haber-Bosch, and electrolysis with low temperature plasma. You see the contributions, that are the positive values to the life cycle, and the negative values that are the so-called credits. And the message of this slide is credits pay off. So if you make electrolysis, you have to go for oxygen credits, and it's a difference if a company like Siemens does it or if you make electrolysis at a farm. Who does at a farm need pure oxygen? You have to think about this, otherwise the technology will not work. And renewables also pay off. That's what we clearly see. Come a bit to the end of my talk, still some slides, but I will quickly go through it. We made an own software, which we want to make commercial now. We want to sell that software. It's computing, and it makes million solutions, and it needs half an hour typically to find the cost effective. And these are just some of the equations here, just to give an overview. This is how the software looks like. It's made on the format of the Ezell scientific cost computing platform, which is quite commonly taken for all kinds of supply chain softwares. And it's made by a university center who works for Telstra or all commercial center to optimize their mobile communication. We also make data collection with farmers, so we get their private data. We have to sign agreement with them. And we finally studied 120 supply chain cases. Yeah, that is what you should do if you have a software making just one case. Then the software is simply not justified. I come to the end to these results over here. So here we have the case of the central hydrogen production in Alice Springs, we assumed, just because that's the center of Australia. And we have local ammonia production. And we have the costs for the different technology combinations which are introduced previously, left conventional, and it gets more and more innovative to the right. And you see the costs go higher and higher on the right. Not surprisingly, the innovations are not there. But if you know the world market price of ammonia is around $320, it fluctuates always per ton. And what we've shown here is not a price, it's cost, so don't mix that. But still, you see, we are at least in a range which is close to commercial with the thermal plasma for sure, but also for the water electrolysis, Haber-Bosch, with a certain optimization under certain conditions. Now, if we combine the hydrogen supply locally and the ammonia supply locally, so hydrogen is not central anymore, it gets even better in the cost, and that is what it should be, because we eliminate the transport, and you see we have costs minimally around 228. As a reminder, the ammonia price is $100 US dollars higher worldwide. So basically it shows that the technologies which we consider are not far from commercial, and the companies who build it, they make commercial plants. Long ago I made this project Africa, submitted to European Union. Africa needs most fertilizers. Here's the world hunger. It has a population growth. So that is a focus of our work. So we have also a little bit social ambition. And the plasma plant was brought to Uganda. They operated it there. And then you see, we also work here very heavily on space architect. That is a very serious business. And the first Australian-led ever experiment on ISS, this is led by me and by the University of Adelaide. And you see here's this picture of the sample flowing in the International Space Station. And very large, we are underway to present at the Royal Adelaide Show, which is South Australia's largest event with 500,000 visitors. The Clare Valley truck farm, and if you ask where's a truck, in the upper right, this yellow object there, that is a truck near the farm, which carries, and you see we have many more figures. This is not finished. 5 students from the architecture school work for 3 months on the old economy model with the long trains and the new economy model. So we try to be transdisciplinary to make other people aware of what we are actually doing. Thank you, and I look forward to your questions.
Thank you. It was a spectacular section. Few questions from audience. Professor Dr. Liley, dear Prof, how can the carbon percentage in hydrogen generation be controlled to guarantee its purity and efficiency?
That's a very good question. The point is the monolith process, I think that's what we talk about, the thermal plasma, was basically invented for the carbon, I said it. Hydrogen is only byproduct. So initially the focus of monolith company was on making dedicated qualities of carbon, and there's big difference. Yeah. So don't mix that. That is not biochar. That is levels better than biochar and can be used for totally different purposes than biochar. And indeed, you can control that by very dedicated process optimizations, which I don't know. But then you set the price of the hydrogen higher. Yeah? You have to make a bit choice. If you make a medium quality carbon product and you go fully for hydrogen as a product, or if the carbon product is your seller, then you make it best. But then the hydrogen price might be higher and used for different purposes.
Thank you, Prof. One more question from Dr. Lina. Great talk, Prof. Volker. Based on your experience with industry, what are the major advice you can share when it comes to connecting the pure science and theories with industrial fields and market?
Yeah, that's a very good question. I like that, and thank you. The point simply is, look, I could sell my microplasma, and the world would see no change in the next 10 or 15 years. Yeah, but we need to work on such things. Don't misunderstand me. If we don't have that vision, we never will make game change. But what I also do in parallel is to use existing technologies, which some people know. Mitsubishi and SK Corporation, that's the largest Korean chemical company, they invest heavily in monoliths. They know it. But how can a farmer knows it? How can a farmer in Africa know monolith? And the whole thing is more complex than just knowing their email address, you know. So there is a kind of knowledge transfer. And I can also not do this alone. Yeah, we have a change manager who sells credit. He's like a stock exchange manager. And we have a farmer in the team, and we have more people. So it only goes together. So if you know what's the definition of transdisciplinary is public-private partnership, then it only goes in this way. And you have to be open for this, and you have to climb sometimes in dirty holes to look at the plant roots. You cannot change the world from the desktop. That is my answer.
Okay, last question from Dr. Laili. Professor, could you kindly comment on the expense of large-scale hydrogen production, infrastructure expenditures, bulk storage, transportation and distribution, safety consideration, and supply-demand uncertainty matching?
Yeah, thanks, a good question. Then let me start with the last one. We have COVID, and we suffer a bit from the world economy because not all is so accessible anymore than it was. So there's a large initiative in Australia on resilience, also on critical minerals. That's the next big topic in Australia. So on resilience, self-sufficiency, and local production, that helps us. People are willing to pay more, naturally, because if you do it finally, you will pay more, a bit more. And we calculate on the 4 scales which I mentioned, central, local, regional, and at farm. We calculate the costs. And for some, we have some models, a 0.6 exponential decrease, but for some, it's pretty unsure. So we try our best to make the modeling as precise as it is. But naturally, you will have higher costs with smaller plants. You cannot betray the economy of scale and Moore's law, but you have to get the payoff by the credits. That is so we have to know about credits also. And
thank you for your patience. Thank you for the explanation. We appreciate the valuable time and patience you have shown today. Once again, I thank you on behalf of MICN 2021. Thank you again.
Thank you. Bye-bye from Australia.
Thank you. Sorry for the inconvenience to you. Okay, I accept my apologies. Let's resume towards our next technical section. It will be my honor to invite, and it's my privilege to introduce distinguished Professor Dr. Lakshmikantam, Indian scientist and Director CSIR IICT. Professor Lakshmikantam has completed PhD degree in the year of 1982 at Guru Sastra University, India. She served as a director at CSIR IICT Hyderabad. She is an adjunct professor at Tezpur Central University, Assam, and RMT University, Melbourne, Australia. She is a fellow of Indian National Academy of Science, India, J.C. Bose Fellow of the World Academic Science, Italy, and Royal Society of Chemistry, UK. Her awards include Goyal Award, Applied Science, Guru Sastra University, Indian Chemical Council, ICC, DM Trivedi Lifetime Achievement Award, Eminent Scientist Award, Catalysis Society of India. She is a member of scientific councils like DST, DRDO, GIL, IIT Hyderabad, CSIR, DAE. She has 37 years of experience in the research, design, and development of catalysis for innovative green and economical process for chemical industry. She has authored more than 347 publications, 52 patents, and 5 book chapters. I would like to invite distinguished Professor Dr. Lakshmikantam to share her ideas on today's topic, development of efficient catalysis for sustainable chemical industry. Welcoming, ma'am.
Yeah, thank you, Suresh, for the nice introduction. And I thank Professor Noor and Professor Mohammed for inviting me the Malaysia International Conference of Nanotechnology and Catalysis. Thank you very much for inviting me. And today I am going to speak about the development of efficient catalyst for sustainable chemical industry. And greetings from Institute of Chemical Technology, Mumbai, India. And I am a professor in Institute of Chemical Technology, Mumbai from 2015. And I finished my tenure as a director at IICT in 2015. So my affiliation is pronounced wrongly because now I am in ICT Mumbai as a BP Godrej professor. Sorry for that inconvenience. And the Institute of Chemical Technology was opened in 1933 under the Mumbai University as UDCT, University Department of Chemical Technology. And in 2005, it has become autonomous, and 2008, it was given the university status, and it is the state-funded university. And Institute of Chemical Technology, you can see that we shall be creators of sprouting knowledge and design cutting-edge technologies that will have the greatest impact on society and benefit mankind at large. And when you name of the Institute of Chemical Technology, you can see there are 600 entrepreneurs from the Institute of Chemical Technology. You can see the Reliance Industries chairman, Mukesh Ambani, is the alumni of our ICT. Like that, you name any industry, Garada, Reddy Labs, or in the Avra Labs, you can name any industry. They are all alumni of the ICT. And coming to IICT, I spent my 32 years of my research and gave the service to IICT, that the Institute of Chemical Technology, that is IICT. And this is the institute under CSIR, Indian Institute of Chemical Technology, and this is an institute dedicated to serve the nation in the area of chemical sciences and technology. And I always start my lecture with the Mahatma Gandhi's word, that is, there is enough for everyone's need, but not enough for anyone's greed. So we have to think about the sustainable development, and chemists have to play a major role in this. And also then coming to the Abdul Kalam's words, our earlier president, and you can see that technology, unlike science, is a group activity. It is not based on individual intelligence, but on the interact intelligence of many. And coming to that world chemical market, you can see the world turnover of the US dollars is $4.1 trillion in 2013, and it is in the 2021, it is $5.1 trillion. And coming to that, you can see the basic chemicals, that is petrochemicals, fertilizers, and pharmaceuticals, and specialty chemicals like dyes, pigments, agrochemicals, insecticides, herbicides, fungicides, and other crop protection chemicals, and biotechnology, biopharma, bioagri. So you can see the $5.1 trillion US dollars of the chemical industry turnover. And coming to that Indian chemical industry, you can see that there are the basic chemicals 53%, and agrochemicals, specialty chemicals, and pharmaceutical 24%. And the size of the Indian chemical industry is $108.4 billion, and it is the 6th largest in the world and 3rd largest in Asia, and it accounts for 3% of the global chemical industry. And why catalysis? And you can see the catalysis by design, and you can see that there are organocatalysis, heterogeneous catalyst, homogeneous catalyst, biocatalyst, polymer catalyst. And the important in catalysis is that you have to model theoretical tools to catalyst design, and also you have to see the characterization, how you design a the catalyst, and the catalytic reaction engineering. These are all important in the 21st century. And again, you see the catalysis opportunities and challenges are unlimited, and the humanity top 10 problems are energy, water, food, environment, poverty, terrorism and war, disease, education, democracy, and population. And you take the catalysis, energy, you need the catalyst, and in water, purification, you need the materials, and again in the environment, yes, you need the catalyst, and also disease, you want to make any pharmaceutical intermediates you need. So you can see the catalysis is a fascinating science, and it has the potential to solve the majority of the problems the world is facing today, directly or indirectly. And coming to the catalyst, and the chemical industry depends on the catalyst, and we depend upon chemical industry for our 21st century life. And 90% of the process in chemical industry uses the catalyst, and the catalyst sales were in between $20.6 billion. And everybody knows what is the catalysis. The rate of the chemical reaction is affected by the presence of a substrate, which it remains unchanged by the reaction. Phenomenon is referred as catalysis, and the substance involved is the catalyst. And what are the key characteristics of a catalyst? You can see the good activity, high selectivity, long operating life, and compatibility with the process, and robustness and low cost. So if your process is very good, but your catalyst is very expensive, then you cannot commercialize the process. And you should see that the catalyst should be low cost. And coming to that, you want to measure the catalyst by design. You see the catalytic properties, you have to see the activity and selectivity, and the chemical properties, oxidation state, acidity, surface composition, and the physical properties. You have to see the surface area, pore structure, and pore density. The ideal synthesis is really atom efficient. It should be safe, one step, no wasted reagent, 100% yield, and available materials environmentally acceptable. And the reaction is the quantity of the products obtained by the theoretical maximum quantity of the product, and selectivity is the quantity of the desired product and the quantity of the substrate converted, and E factor is total quantity of the waste and quantity of the product obtained. And you can see, for example, when you are doing a reaction, A plus B gives C. And if there is D, that is unwanted product, then the selectivity will be less. So you have to aim A plus B gives C, then the reaction is very selective. And you will go for the oil refining, you can see the product tonnage is very high, 10 to the power 6 to 10 to the power 8. And whereas the E factor is very low. When you go for the bulk chemicals, again, tonnage is 10 to the power 10 to the 6, and the E factor is 1 to 5. Whereas you go for fine chemicals and pharmaceuticals, there are a number of steps involved, and they may use the reagents, there will be no catalyst, and you can see the E factor increases, and the lower the E factor, higher the process efficiency. And you can see the periodic table of elements, and you can see the molybdenum, ruthenium, rhodium, palladium, silver. They are all very good catalysts. And the supports, you can see the titanium, alumina, carbon, and silicon as a supports you can see. And there are promoters also, zirconia and other promoters you can see. And you can see the poisoning as you do the petrochemicals. There is a sulfur poisoning, and again you go for the mercury poison, and which kills the catalyst. So these are the poisons in the catalytic thing. And also when you go for the solid base catalyst, and you can see the acidity and basicity, and there may be some needs Lewis acidity, some needs Lewis basicity, some needs the Bronsted basicity or Bronsted basicity. So you can design a catalyst depending upon the acidity or the basicity of this one. And you see the chemistry for healthcare, you can see the asthma, corticosteroid, cancer, Taxol, penicillin, infections, Alzheimer's, donepezil, aspirin, for pain and headache, AIDS, AZT, diabetes, insulin, and malaria, chloroquine. You can see the chemists have synthesized various molecules. So without chemists, yes, you cannot help the healthcare people. So you need chemistry is very important. And when you go for the Catalysis and Nobel Prize, you can see Heck and Negishi, Akira Suzuki, they got the Nobel Prize in 2020 for palladium catalyzed cross coupling. And you will ask, what is that catalytic reactions, Suzuki and Heck reactions, why they are important? And these palladium catalyzed cross coupling reactions are used in worldwide and as well as in the commercial production, for example, pharmaceuticals and molecules used in the chemical industry. And you see that you take an aryl halide, it may be a bromo compound, ido compound, chloro compound, and react with an olefin, you will get the stilbene derivatives. And you see that when you are activating the bromo and ido compound, you just need a palladium chloride and triphenyl phosphine, and you can get the stilbene derivatives. where you want to activate the chloro compound, you will need the special phosphines, phosphopalladiocycle, phosphonium salt, electron-rich phosphine. And why these phosphines are moisture sensitive? There are number of steps involved to make this one. So what is the reaction? Heck reaction is important. You can see the herbicide prosulfuron, you need a Heck reaction, and anti-asthma segment singular as Heck reaction. And you can see the anti-cancer reagents, you want Heck reaction is important. And relabeled HIV infections, you can see the reactions, any reactions you can see without Heck reaction, you cannot make these compounds. And again, you can see anti-inflammatory drug, nephroxin, you can see the Heck reaction. And again, octyl methoxycinnamate, which is used as a sunscreen agent, and also you can see the optical brightener, and this also you can need the Heck reaction. So what we think that phosphine-free catalyst, we thought that phosphines are very difficult to make, multi-step, and they are moisture sensitive. So we thought of making the phosphine-free catalyst. And you can make these dicarboxymate dipyridyl ligands, palladium complexes very easily. You can take a phenylalanine, or you can take a valine and react with the thionyl chloride, and then picolinic acid and ethyl chloroacetate and lithium, and you will get the acid, amino acid. This amino acid and react with methylaminopyridine in presence of dicyclohexyl carbamate, you will get the immediate ligand, and then you react with palladium salt, you will get the palladium immediate complex. And this one is a multi-step, but there are not moisture sensitive. You don't need any special precautionary measures, and it is stable for years together, and it can be easily made. And we have given the crystal structure. And what is the important? I already told that activation of the bromo and ido compounds is very easy, but the activation of the chloro compounds is difficult. So we used this catalyst, and we can activate the aryl chloride, and you react with olefin, you will get the very good yields, and the turnover number is also very high. So this is a non-phosphine complex we made. And again, what we thought is hydrotalcite. These are nothing but magnesium, aluminum, mixed oxides. Anybody can make in the laboratory. And why we have selected hydrotalcite? Because this is a basic, and the phosphine is a basic, so you can select this catalyst. This can be easily made in the lab. And what you have to do is you take a magnesium chloride and aluminum chloride, and you react with sodium hydroxide, and you make the pH 10, and you will get the mixed magnesium aluminum chloride hydrotalcite. And then again, the exchanger, you react with tetrachloropalladate, and you will get the exchanger palladium chloride. Why we have selected LDH? It is a basic, so it likes as a support like the palladium. And then we make the palladium complex, and then hydrogen hydrochloride we reduced, and you will get the palladium 0. And you can see the TEM image palladium nanoparticles is 4 to 6 nm, and we have characterized the XPX spectra, and to show that palladium is in the 0 state. And the important is we did the reaction of the chloro compound, and you see the chloroaryl halide and react with olefin with our catalyst, and you can see this thing. And this catalyst can be very easily recovered and then can be reused. And again, Suzuki coupling reaction, what is important, they have also got the Nobel Prize. And see, you can react an aryl halide with boronic acid, you will get the biphenyl. This is the Suzuki reaction. And why Suzuki reaction is important, you can see the fungicide and treatment of rheumatoid arthritis, Crohn's disease, and psoriasis. Without Suzuki reaction, you cannot make these pharmaceuticals. And also you see nowadays people are having the Alzheimer's disease. So Suzuki's reaction is very important to make this thing. And again, you can see that everybody has hypertension, high blood pressure. And without Suzuki reaction, you cannot make any reactions. Losartan, candesartan, olmesartan, these are all made by Suzuki reaction. You can see the importance of the Suzuki reaction. So the same catalyst what we used for the Heck reaction, you can see you can take the bromoaryl compound, and you can see the boronic acid and react with one. And here you can see the room temperature 12 hours, you will get the biphenyl very easily. So this also we can make it to catalyst. And also we did the biomass conversion to chemicals and see the linoleic acid converted into velrolactone, and you can see the velrolactone is used for the green solvent. And here what we did is we made the copper nickel magnesium hydrotalcite. Again you can see we have made the hydrotalcite catalyst, and we have used for this one, and it is very easily you can prepare, and we have completely characterized the catalyst by XRD, and you can see the formation of the copper nickel alloy formation after the reduction. First you make the catalyst, you make the calcination, and then you reduce before doing the reaction with hydrogen, and there is a formation of copper nickel alloy, and then we have characterized the copper catalyst also, and see the copper 2 plus oxidation state, and then we have used for the reaction, and you can see the copper nickel magnesium hydrotalcite catalyst, because the other catalysts have high temperature, high pressure, but whereas 140 degrees and 30 bar pressure, you will get the linoleic acid conversion 100% and 100, and you can see the thing we can make it. And again you can see we did the CN bond formation reaction also using our own catalyst, and you see why the CN bond formation are very important. You can see anything antibacterial agent like linezolid, benzolactam, all these molecules are pharmaceutically important intermediates, and you have to see that CN bond formation reaction is very important. And here again we have selected another catalyst, which is apatite, and you see that our bone is made up of this apatite, that is nothing but calcium hydroxyapatite. These are the main constituent, and anybody can make these apatites very easily, and these are biomaterials, and you can see the catalytic application. Again, it is a basic materials. So what we did is materials are known, reactions are known, how you design a catalyst, how you use for a reaction is important. And you can see the calcium nitrate and treated with the ammonium dihydrogen phosphate, and you will get the calcium hydroxyphosphate. And this one you can see calcium hydroxyphosphate. If you want more basicity, you react with ammonium fluoride and you will get the fluoroapatite. And if you want, you can also react to tertiary butoxide, you will get the tertiary butoxide apatite. And we reacted with copper fluoroapatite. And why this reaction is important, you can see the any imidazole you take, and you can activate the chloro or fluoro compound with using your apatite catalyst, and you will get the substituted imidazoles. This also we have published in JACS. So you can see the apatites you can take, and you put the metals, and you can do the 3-component reactions and base Hillman adducts, any reactions like that. You take hydrotalcite, you take the asymmetric dihydroxylation, you can make alylation. So simple support you can make very easily, and you will put your metal and you will do a number of reactions. And then again we went for the nanomaterials, and we have a collaboration with Professor Klabande, and he has given the nano magnesium oxide, because you can see the nano magnesium oxide high surface area, and it is a polyhedral in shape, whereas the commercial nano magnesium oxide is cubic in shape, and the surface area is 30. And we have selected this nano magnesium oxide, and you can see these are Bronsted basic sites, and these are Lewis basic sites, and these are Lewis acidic sites. So based on this one, we have done the reaction Claisen-Smith condensation. You can see you take an ketone and you react with aldehyde, you will get the chalcones. Chalcones are very important. They have anti-inflammatory, anti-malaria, and anti-protozoal activity. And you can see when you use the nano magnesium oxide, 97% in 12 hours, whereas the commercial magnesium oxide, 50 hours. We don't know why it is. Then what we see, I told you that Bronsted basic sites are important, as well as the Lewis basic sites. When you do the reaction, it takes 12 hours, both sites are there. And when you silylated these Bronsted basic sites, and reaction takes 20 hours, and instead of 12 hours, and it takes 20 hours. That means the Bronsted basic sites as well as the Lewis basic sites are important to make the reaction. And you can take this nano magnesium oxide, and you can make the Claisen-Smith, Strecker reaction, asymmetric, cyanosilylation, organic carbamates, Wittig reaction, Wordsworth reaction, you can do wonders with nano magnesium oxide because of this size. And again, you can go into that one, and you can see that we have developed a technology, and you will ask what you will do. And when I was IACT, we have developed a technology for para-tertiary butyl toluene and para-tertiary butyl benzoic acid and methyl para-tertiary butyl benzoate. What is the use of para-tertiary butyl toluene? You can see para-tertiary butyl toluene is used in the solvent and intermediates for organic synthesis, and benzoic acid is used as a catalyst and additive for cooling, lubricant, and antioxidants, and also the methyl para-tertiary butyl benzoic is used as a flavoring agent, masking agent, and it is the important ingredient for making the sunscreen agent, and we have all patents. And what we did is, you take a toluene and you react with isobutylene to get the para-tertiary butyl toluene, and usually we have developed exclusively single isomer, and we have demonstrated the process in 2013 to industry. And then we have put a pilot plant in IACT, 12 tons per day, and you can see the pilot plant was designed and erected, and we have demonstrated in 2014. And similarly, the para-tertiary butyl toluene is oxidized to para-tertiary butyl benzoic acid, and also the process demonstrated, and we have one catalyst and we have demonstrated. And you can see, based on our results, and they have, industry has put a commercial plant, and they are making para-tertiary butyl toluene 4,000 tons per year based on our technology. And they are also making the para-tertiary butyl benzoic acid 3,000 tons per year, and this we have given to the industry. And when you are developing any process, you have to see, we have to match all the industrial specifications, and we got all the market specifications, our product and market product, and you can see we matched all the specifications. And also, when you are giving a process, and people will see that what is the economics of the process, and we have to show in the pilot scale consumption of the raw materials for the kg of the para-tertiary butyl benzoic acid, and you can see the price of the, and you can see what are the raw materials, catalyst, acetic acid, and you can see 94 rupees, and whereas the price of PTBA is 245, and this is for 1 kg, and they have already producing 4,000 tons, and you can see that how it is economically viable. If it is not economically viable, nobody will take your plant, and nobody will commercialize it. So this is, we have demonstrated all, and then we got the technology award also from Government of India for this process, and they are producing. So what is the future of catalysis? You can see, primary role of catalyst is process intensification and energy savings, economy, environment, and the new challenges before the chemists and engineers today is to develop innovative catalytic process for utilization of biomass for fuels and chemicals to address the issue of sustainability and fast dwindling petroleum resources. And goals and challenges of the catalytic scientist is the vision and technology targets is the selective oxidation, alkane activation, and the byproduct and waste minimization, stereoselective synthesis, functional polymerization, alkylation, alternative feedstocks, and renewables. As already told, that we are working on the biomass, and the biomass to chemicals is an important attractive feature. And these are the events at IACT. These are all the past directors when I was a director at IACT. And this is our with the director and Professor Nayori, Nobel laureate, when he visited ICT. And also my acknowledgement is ICT Mumbai, and I was a Godrej professor, so Godrej Consumer Products and JC Bose Fellowship, and CSR IACT Hyderabad, where I spent 32 years of my life. All my collaborators and students, RMIT University, Australia, Professor Suresh Bhargav is we are working together, and Tejpur University and the University of Newcastle and the present team. And thank you. Thank you for the attention.
And delivered the lecture for us. I now open the floor for question.
No question. No
I
questions.
think no questions. Yeah. So
Yeah.
once
Thank you.
again, sincerely thank you for accepting our invitation and for
Thank
your
you, Suresh.
valuable, sharing with us the result and thoughts, your research findings during your lecture. Behalf of MICNC, thank you again for your time, ma'am.
Thank you, Suresh. Thank you.
One question, Chegu, great talk from Lakshmikant concerning the Bronsted and Lewis basic sites on these heterogeneous solid catalysis. What proper method to determine the amount of those sites?
Yeah, yeah. We have 3D memory disruption methods. We calculate. Yeah. TPR, TPD. Yes.
Okay, okay. Thank you, ma'am. Thank you again for your time.
Thank you. I can log out. Yeah.
Yes,
Thank. Thank you.
let's take up again with our next technical section with the resource person, Professor Dr. Juan Jeffrey, University of Malaya, Malaysia. It's now my privilege to introduce Professor Dr. Juan Jeffrey, graduated with BS degree in chemistry from University of Malaya in the year of 1991. He then furthered his studies at the University of Southampton and was conferred a PhD in electrochemistry in the year of 1997. He started his career as a senior lecturer in the Department of Chemistry, University of Malaya. In the same year, was promoted to associate professor in 2003 and professor in 2011. He is currently supervising more than of 10 PhD students and has co-supervised 12 PhD students to completion. His research areas are electrochemistry, material science, and nanotechnology. Has published more than of 130 research papers. He has managed to establish research collaboration with several groups like South Korea, Australia, and Iran. May I now take the pleasure of inviting and requesting Professor Dr. Juan Jeffrey to deliver the lecture on nanocellulose for electrochemical application. Let's have the pleasure of listening to the honorable and great speaker.
Okay, can you all hear me?
Yes, yes, Prof.
Okay, so I just start with electrochemical applications of nanocellulose. So basically, nanocellulose is a biopolymer synthesized in plants, microorganisms such as bacteria, animals. When you refer to nanocellulose, meaning it is basically a nanostructured formation of the cellulose material. Cellulose is basically found in in plants, so it's basically utilized in in many aspects of such as photonics, composite medicine, modifications, even biometric. It is a bio resource. A very good, a very abundant material found in plants. So when you mention nanocellulose, basically it is a form of nanofibers, typically between 20 and 100 nanometers in diameter. Okay, so basically, nanocellulose will actually rival carbon fiber for three-dimensional printing. Basically, it can be used in 3D printing as a resin. And one of the advantage of nanocellulose, I just mentioned NC. It is abundant. It is available abundantly, and it is a cheap resource. So this is the market projection of nanocellulose. Basically, when you have more end users of the material, when you have, like, for example, widely used, the market value is basically, it tends to rise with time. And Malaysia is also it is basically one of the countries which have a very huge biodiversity. Like, for example, you have lots of palm oil plantation, and this is a very good source of cellulose material. Yeah? And this is the structure of the cellulose. Basically, it is a polymer structure. Okay, so nanocellulose. So what it has, relevance in electrochemistry. Yeah? So cellulose, like chitosan, other biopolymers are good ionic conductors. Okay, so but it is an electronic insulator, because conductivity, you have ionic conduction, you have electronic conduction. Okay, so it can be used as polymer electrolytes in battery, because due to its ion conduction in dye sensitized solar cell, you will see some examples. and has electrodes in electrochemical sensors. And these cellulose fibers, it has very large surface area. It has lots of functional groups such as OH functional groups, and so these are the basis for the use of nanocellulose in electrochemical sensing via the chemically modified electrode method. Okay, so like for example, when we move to electrosensing, electrochemical sensing, it is always has to do with chemically modified electrode. Okay, and that electrode has to be conducting. But nanocellulose is not an electronic conductor, but it is an ion conductor. So that is the the beauty of nanocellulose. It is not although it is not an electronic conductor, but it can be used as an electrode when it combined with other electronic conducting materials. So in our experiments, we have used nanocellulose has an electrochemical sensor for drugs. Like for example, this drug which people take, it is freely available in pharmacy. The pharmaceutical, it is being marketed in the pharmacy, and we can use this material as our analyte, our target analyte, using nanocellulose as the the electrode material. So this is the electron microscopy or FESAM for the nanocellulose. So this is being done by one of our PhD students in chemistry and nanocad. Yeah. So you can see that the nanocellulose has basically it's not a nanofiber, but when you combine with, for example, MWCNT, like for example, multi-wall carbon nanotubes, and then you get the nanocellulose formation, because the cellulose basically binds with the CNT, and it becomes a fiber in structure. So you can see the second on the right and on the bottom, it becomes fiber when you combine with the MWCNT or multi-wall carbon nanotube. So this multi-wall carbon nanotube is served as the base for the nanocellulose to bind with it. So when it binds with it, now you have an ionic conductor and an electronic conductor has a composite material. So then you can use it for many things, such as electrochemical sensing. So these are the powder XRD diffraction results. Okay, nanocellulose, if you can see the powder XRD, it is basically superimposed the nanocellulose, because for any crystalline material, then you get a peak in the powder XRD. So when you combine the nanocellulose with the MWCNT, then you get two double peak, as you can see in the top of the figure 3. Yeah? Okay, so, and this is the FTIR. So because due to nanocellulose has an abundance of OH group, then you have naturally in the 3300 you get a band for OH group. But as you can see, there is not much difference between FTR or nanocellulose and the cellulose material. The only difference is the dimension of the nanocellulose. Basically, it is less than 100 nanometer. Diameter. Okay, and this is the FTIR of the MWCNT. MWCNT alone. So we combine these two materials to get the our nanocomposite. So one of the most important characterization in any electrochemical sensing is the use of electrochemical impedance spectroscopy. Yeah? But this is not the only characterization we must use in our experiment, because we must couple, because this is an AC technique. It is an alternate current technique. So when we do any experiments in electrochemistry, AC technique, we must always check with DC techniques. Okay, so this is the EIS technique, which is the AC technique, alternate current technique. So this result shows that our composite electrode, the nanocellulose and the CNT, it has a slightly lower electronic conductivity compared to the GCE. GCE stands for glassy carbon electrode. Glassy carbon electrode is the electrode which we use in our experiments, and GCE is basically inert. So that's why you see the blue dots for the GCE. it has very large resistance because it is a slightly inert material. It is not very reactive. So the surface of the GC has to be modified with any other electronically conducting material or an ionic conductor so that it can be activated as a sensor electrode or for many other things. Okay, so this is AC technique. So then we move into DC technique, which is cyclic voltammetry. This is the one of the most preliminary experiments we perform in electrochemistry. So we can see that the nanocellulose, the multi-wall carbon nanotube, it has a higher current compared to the CNT electrode only, and compared to nanocellulose and compared to GC. The GC gives us the lowest current because it is an inert electrode. But once we activate the glassy carbon, or the black line, then you get a higher current because now the surface of the glassy carbon has been activated by the incorporation of the nanocellulose and the MWCNT, the material. Okay, so now you get it activated. So this peak is for the peak of our analyte, the diclofenac sodium, or DCF. DCF is the analyte. The drug which is being used as the analyte for the sensor development. So people take DCF, for many purposes because it has a pain relief, as there are many, but also there are many side effects of the DCF. The DCF is basically given here previously. Okay, so this DCF is sold in the pharmaceutical shop. So people take it as a pain relief and other remedy. But of course, too much of it can actually give you side effects. So that's why there is a need to actually monitor the concentration of DCF in the human body, like for example, in the body fluid, plasma, blood, urine, and so on. And also people use, when people have this drug, they don't want it, they just throw away. So that's why you have DCF in the environment. So when this medicine is in the environment, then it can actually react with something else, and it become, like for example, endocrine disruptors and so on. So this is a very common medicine, just like paracetamol, Panadol is when you don't use it, they simply throw it away in the environment, and then it gets absorbed in the environment, and then it creates more problems for for consumers, like for example, water resources or food resources. So that is why there is a need to actually monitor the concentration of these type of drugs in the human body and also in the environment. Okay, so that's why we develop a sensor for for sensing of the DCF material or DCF drug. Okay, and again, this is basically the CV. Our results in the voltammetry for DCF monitoring using our sensor electrode, and we have very good results. So this shows that there is a very good response on the sensor electrode by using the DCF analyte. Okay, so the two important things, like for example in sensing, is the two S. One is sensitivity and one is the selectivity. Basically, when we develop a sensor electrode, we must ensure that sensing electrode has very good sensitivity, meaning it can go at very low detection limits, like for example, a few nanomolar or less than nanomolar in solution. And also it has very high selectivity, because when you measure a real sample, then we have, like for example, various contaminants or interference. Like for example, DCF can be interfered by, for example, dopamine or acetaminophen or any other drugs which also being consumed in the human body. So this is a further look at the mechanism of the DCF oxidation by very different pH, and we found out that pH 4 has pH pH 4 has the highest peak current. So that's why we select pH 4, because it has the highest peak current for the DCF oxidation or electro oxidation. Okay, therefore, so then we move into differential pulse voltammetry. the advantage of using differential pulse voltammetry is that DPV compared to CV, DPV is a pulse method. Okay, so if you notice, like for example, this slide and this slide. This slide is using cyclic voltammetry. You notice that the background current is very huge. Okay, there is an elevation of the background current. Okay, this is due to the charging current or the electrochemical double layer capacitance. That's why you have the elevation of the background current. Okay, but when we use DPV, you notice that the background current almost reduces to zero. It degrades to zero, meaning there is a perfect baseline. So because that's why we use DPV, differential pulse voltammetry, because it can actually eliminate the charging current. Because the charging current is the one that what you call increase the baseline. So when we don't want to have the charging current, we use pulse method. And the best pulse method is differential pulse. Okay, there's also another method which we call square wave voltammetry, but that is people also use it. But most people use it DPV because it has very high sensitivity. Yeah. Okay. So this and further we actually run the experiment to study the selectivity. So we actually also determine DCF in the presence of dopamine and ascorbic acid. So we see that the ascorbic acid and the dopamine does not the peak of the ascorbic acid and the peak of the dopamine does not interfere with the DCF. So we can be sure, the DCF occurs at beyond 0.6 volt, whereas the other two interference occurs at below that potential. So it does not interfere with the DCF potential. Okay, so when we actually perform experiment using electrochemistry, we don't always run our experiment and get the result, but we try to propose a mechanism, because this nanocellulose is very polarized with OH groups. So therefore it attracts any analyte with carbonyl group or a carboxylic group or hydroxyl group. It attracts and then it binds it together, and then you get the electron transfer. But this is our most probable electrochemical oxidation mechanism. So in our experiment we have done, we shows that it shows that the surface diffusion, once the analyte gets absorbed onto the surface, then there'll be surface diffusion of the analyte onto the cellulose itself, because the cellulose is a very good binding agent for the DCF molecule or the DCF drug. That's why when the molecule or the drug binds with the cellulose the surface on the electrode, then you get the electron transfer. The electron transfer will occur after the binding of the analyte with the cellulose on the electrode. Okay, so this is our also another mechanism being proposed. Basically, when people perform experiments, when they get different results from other people, then they propose a different mechanism of oxidation or reduction. Okay, so when we compare our work with others, we have found that our detection limit is very, very low, 0.012 micromolar. Meaning it is almost close to nanomolar. So compared to other works, the works of other people. Also the linear range is also being expanded from 0.05 to 250 micromolar. But our detection limit is quite low, 0.012. Is among the lowest in this So meaning when you have a very low detection limit, meaning you can actually detect very low amounts lower amounts of the analyte in the solution. So that is the advantage of very low detection limit. So basically, the people have also reported below than 1 nanomolar, meaning can go to 10 minus 10 molar of sample in solution. So this type of work is very useful for, like, for example, determination of drugs in the human body or the human plasma or human urine, because electrochemical determination is quite cheap compared to other methods. Like, for example, when you have GCM is a very expensive equipment, and it need to be performed by a highly trained personnel. And like, for example, liquid chromatography, it also a very expensive equipment. But the advantage of electrochemistry is that we can actually fabricate in situ, electrochemical sensors, like for example, portable electrochemical sensors. So Dr. Leo also from medical faculty has also ventured into the area, and she also published some papers of portable electrochemical sensors. So the advantage of electrochemical sensor is that it can be portable. It can be run on a DC power supply, and you can actually bring it in, has for on-site detection of the drugs. So compared to other methods, like for example, GCMS or LCMS, it is very expensive. Then you need to bring sample to the lab. But in electrochemistry, you can actually fabricate portable sensors which can be brought to the patient itself. So there is no need for a very high powered power supply and so on. Okay, so and this also is basically by using differential pulse voltammetry, and we have seen that our sensors are basically within the range. And also this is another result of our results. Okay, and also, like for example, one of the most important electrochemical sensing is that sensor has to be stable for after a few weeks. So we have actually performed experiment. On the first week, and then we put the sensor into storage for a few weeks. We see that after 2 weeks, the signal just slightly reduced, meaning not much of a reduction in that signal. Okay, so now that is for the electrochemical sensing. Okay, so now we go into other electrochemical application of nanocellulose. So there is one work being published in using nanocellulose as a electrode material for supercapacitors. Okay, we have also done supercapacitance work, but not using nanocellulose. But this is a result of supercapacitance or supercapacitor utilizing nanocellulose as the electrode material. So why does nanocellulose can qualify as a supercapacitor material? Because from the structure, it has an abundance of OH group, and this OH group serves as a binding agent for the ions in the supercapacitor electrolyte. So that is why it can be used as a supercapacitor. Another application is in solar cells. So basically, I'm not involved in solar cell, but some of my collaborators in UKM is involved in solar cell. So this work describes the use of nanocellulose as a substrate in solar cell. Solar cell using nanocellulose, published in scientific report by Zhu et al. And also another work by the same author uses nanocellulose. CNC stands for nanocellulose as a substrate for solar cell, which has an efficiency of 4%. Previously, it was 2.7%. This is basically using I guess it is different type of solar cell, but another one is basically they give 4%, better than the previous result. Okay, so another, so these are basically all the results of nanocellulose being utilized as solar cell. Basically, solar cell is a many type of solar cell, organic solar cell, dye-sensitized solar cell, and the efficiencies are given in this table. Okay, and further on, because nanocellulose is basically a biopolymer, it can be used as membranes in batteries also. So, like for example, this result in Chem Electrochem publishes the use of nanocellulose as a membrane for batteries. So because any battery need a membrane, because this membrane serves as separated between the anode and cathode, and this result gives us an idea about using nanocellulose in battery membrane, because the membrane in a battery basically polypyrrole, and polypyrrole is not polypropylene. The membrane in a battery is polypropylene, and polypropylene need to be synthesized. So this work describes the use of nanocellulose in different proportion with polypyrrole has a battery membrane. And further on, a membrane composed of bacterial non-cellulose and with aluminum oxide has a separated lithium-ion battery. Okay, so this lithium-ion battery also uses a nanocellulose membrane. So this is further applications of nanocellulose in electrochemistry, especially in lithium-ion batteries. Okay, so and finally, nanocellulose has anti-corrosion material. Okay, so this nanocellulose can also be used as an anti-corrosion material, has been reported in Bioresources Journal. And this nanocellulose is being utilized as a material in an epoxy resin and coated into mild steel and used as a protective material against steel corrosion by immersion in 3.5% sodium chloride solution. And the result shows that nanocellulose acts as a protective coating against steel corrosion. Okay, and why does it protect the steel surface? Is that because the abundance of OH groups basically attracts the water, the chloride ion solution, the chloride corrosive ion and the oxygen. It binds with this corrosive agents and prevent the corrosive agent from entering or touching or entering into the steel onto the steel surface. So that is how it protects the steel surface. It binds it and it holds it there, meaning it prevents the chloride ion or the oxygen molecule or water from touching the steel surface. Okay, that is the thing about nanocellulose. So in conclusion, basically, nanocellulose is a cheap, readily available, and environmentally friendly, non-toxic, stable, and ionic conducting material, which has been utilized in much of electrochemical applications such as anti-corrosion coating, battery, membrane separation batteries, supercapacitor, and sensors. The only disadvantage of nanocellulose is an ionic conductor and not an electronic conductor. Hence, must be supported by other electrical conductors such as CNT, graphene, and EDC. But due to the active functional groups such as OH group, which promotes analyte absorption, further application of nanocellulose could be seen in electrophoretic deposition, electrosubstrate in photoelectrochemistry, and membranes in fuel cells. So these are the up and coming application of nanocellulose in electrochemical application. So with that, I end my talk. I would like to thank my postdoctoral student and my postgraduate student, UNICEF Malaysia, and Minister of Higher Education for funding. And last and not least, NanoCat for inviting me as a keynote, a speaker. And with that, I end my talk with Assalamualaikum and good evening. And you have any question, we can discuss later. Thank you very much.
Thank you very much, Prof, for your excellent presentation. Now we have a Q&A section. I now open the floor for questions. There are 3 questions. The first question from Dr. Yusulia. Thank you, Prof, for a great presentation. May I know how do you resolve the hydrophilicity of nanocellulose in your work?
Okay, basically nanocellulose it is a hydrophilic material because there are OH functional groups and also carbonyl. But the advantage is that nanocellulose, although it is hydrophilic, it does not dissolve in water. Okay, so you can actually, like for example, if you want to actually, turn it a hydrophilic material into a hydrophobic material, meaning you need some surfactant. Okay, because like for example, there are many a long chain CH2 group surfactant. And at the end of the surfactant, you have a polar group. When you actually apply this long chain surfactant onto the nanocellulose surface, it blocks the nanocellulose surface and it turns the nanocellulose surface into a hydrophobic surface. Like for example, when you have a long chain CH2 group, and with the end of it, it is you have a polar group. This polar group attaches itself to the OH group, and it turns the hydrophilic into a hydrophobic surface. You can actually modify using a surfactant, and there are many types of surfactant. There are anionic surfactant, there are cationic surfactant, which can be used to modify the surface of the hydrophilic nanocellulose into a hydrophobic, or you can actually increase the polarity of the nanocellulose by chemical reaction, by turning it into, like for example, COH group, because CH group is more polarized compared to OH group. So that's why you can actually modify the nanocellulose surface. So the possibilities are basically endless. You can actually, once you have the cellulose surface, you can modify using chemical reaction, by using what you call surfactant or any other what you call material, like for example, which can modify or which can alter the hydrophilicity or the hydrophobicity of the surface. In fact, you can also deposit what you call a carbon, what you call a metal nanoparticle onto cellulose surface, and that can actually increase the conductivity. You can actually look at different application, like for example, I don't know, maybe supercapacitor, or maybe solar material. Because the beauty of nanocellulose is that it has the OH group. When you have the OH group, you can actually bind with many other what do you call attachment, like for example, what do you call a light sensitive a molecule attached to the OH of the nanocellulose. You can turn nanocellulose into a light sensitive material by attaching by chemical reaction, of course, to the OH group. So you can have many application on nanocellulose. It's just like graphene oxide. No, graphene oxide, your COH group, right? You can actually modify the graphene oxide surface using a metal nanoparticle or any other chemical what do you call a molecule which is UV active or light active. So that's how you modify by using chemical reaction. Okay, I hope that answered the question.
Thank you. Next question from Dr. Asmilina. Thank you, Prof, for this interesting talk. Is there any effect of temperature on the nanocellulose with multiple nanotips properties?
Yeah, unfortunately, we have not done any temperature effect. But as far we know that nanocellulose, because it is a polymer manufacturer, it is stable to high temperature. But of course not very high, not to 100 degrees Celsius. It has stability to temperature effect. It is stable. It has what do you call reasonable stability against extreme pH. Like for example, very alkaline or very acidic. It has a reasonable stability to variation is pH. But we have not done any. Unfortunately, we have not investigated the temperature stability of the nanocellulose composite. Maybe we can actually try for another. In future after this. Thank you very much for the question.
Okay, the final question, Dr. Leo. Thank you for your excellent talk. Prof, may I know what is the acceptable values for the percentage of deviation of your biosensor?
Okay, when we actually look at the stability of the sensor with time, preferably it is not more than, because it depends on the material. Because you have a very sensitive material, then you can degrade it with time. Yeah? But when you have a very stable material, preferably it's not more than 5% for after 4 weeks. But like for example, when you deal with you deal with all these biopolymers, because biopolymers, it is stable until a certain extent. Because like for example, of course, biopolymers is prone to oxidation, right? You know that the OH group can be oxidized to aldehyde or a ketone group. So when you have biopolymers with OH group, then it is not very stable when you put out in the air, because it can be oxidized to a ketone or an aldehyde. So, but the most, preferable is basically not more than 5% after 4 weeks of storage. That is the most, but we have not, achieved this stability yet, because our materials are basically air sensitive. Like for example, biopolymers are very sensitive to air. If you have you have a abundance of OH group, it can be oxidized to ketone aldehyde. So it is not very, it is not material which is it is a material prone to oxidation once you have the OH material, OH group in the in the polymer, because it can be oxidized to aldehyde or ketone groups easily. Yeah? So that's why. But preferably it is not more than 5% after 4 weeks. That is our target, but we have not achieved this target yet, unfortunately.
I think no more questions, Prof. Thank you again for your valuable time and share with your knowledge. So thank you everyone for your time and patience. We are extremely privileged to have all here today. I would like to thank each of you for attending this conference and sharing your expertise with our gathering. I hope that you all enjoy, share, and acquire more knowledge through this conference. So thank you again all. Thank you.